The Dipole Repeller is a cosmic void, a region of nearly empty space, roughly 750 million light-years from us, that appears to be pushing the Milky Way and everything around it in the opposite direction. In 2017, a team led by cosmographer Yehuda Hoffman published a reconstruction of the local velocity field that reframed how we understand cosmic motion and cosmic flows. For decades, the dominant explanation had centered on attraction, on the gravitational pull of the Shapley Supercluster, the Great Attractor region, and the dense knots of matter that tug galaxies toward them. The Dipole Repeller introduced the other half of the ledger, the push. Not from a force, not from exotic matter, from absence. A void so large that the missing mass leaves a measurable imprint on the peculiar velocities of tens of thousands of galaxies, including our own. The Cosmicflows program, the distance compilation that made this reconstruction possible, has since expanded from Cosmicflows 2 to Cosmicflows 4, and, as of 2025, CF4++, with each iteration sharpening the map and deepening the questions it raises about bulk flow, dynamical homogeneity, and whether our standard cosmological model fully accounts for what we observe. What follows is an examination of the evidence. By the end of this video, you will understand what the Dipole Repeller is and what it is not, how peculiar velocities are measured, why underdense regions produce effective outflows in an expanding universe, what the Cosmicflows reconstructions reveal about the balance between cosmic push and pull, and where the data currently stands, including the debates, the limitations, and the open questions that remain after nearly a decade of refinement. If this channel is the kind of content you return to, consider subscribing. There is no algorithm shortcut for depth. Let us begin with the measurement that started everything. The Milky Way is moving. Not just rotating, not just orbiting within its local galaxy group, but translating through space at a speed that, by everyday standards, resists easy comprehension. Planck satellite observations of the cosmic microwave background, the remnant radiation from roughly 380,000 years after the initial expansion, reveal a temperature asymmetry across the sky. One hemisphere registers slightly warmer. The opposite hemisphere registers slightly cooler. The pattern forms a dipole, and it corresponds to a Doppler shift produced by our motion through the CMB rest frame. 620 plus or minus 15 kilometers per second. That translates to approximately 2.232 million kilometers per hour, or about 1.387 million miles per hour. At that velocity, the local group of galaxies, the collection that includes the Milky Way, Andromeda, and roughly 80 smaller companions, covers a distance of about 0.76 light days every year. The number sounds fast, 2 million kilometers per hour. Consider, though, the distance to the Shapley Supercluster, one of the most massive concentrations of matter in the observable universe, at roughly 652 million light-years away. At 620 kilometers per second, traversing that distance would require approximately 315 billion years. The age of the observable universe stands at 13.8 billion years. The speed that sounds enormous barely registers on the scale of the structures that produce it. At 620 kilometers per second, the local group covers roughly 19.6 billion kilometers in a single year, impressive by any terrestrial standard, yet a distance that light traverses in about 18 hours. In the time it has taken you to listen to this sentence, the local group has moved approximately 3,000 kilometers relative to the CMB rest frame, 3,000 kilometers, the distance from London to Cairo every 6 seconds. Step outside tonight, though, and looked at the sky. Nothing would appear to move. The distances between the objects stretch so vast that even at 620 kilometers per second, the apparent positions of galaxies shift by amounts too small to detect over a human lifetime. The motion is real, it is measurable, it is precise, and it remains completely invisible to direct observation. We know about it only because of the temperature asymmetry imprinted on microwave radiation that has been traveling for 13.8 billion years. When Arno Penzias and Robert Wilson first detected the cosmic microwave background in 1965 using a horn antenna at Bell Telephone Laboratories in Holmdel, New Jersey, the signal they measured arrived nearly uniform, the same temperature in every direction to within a fraction of a percent. Years of progressively more sensitive observations followed before the dipole component could be resolved, that slight warm-cool asymmetry indicating our motion. The COBE satellite, launched in 1989, measured the dipole with precision and established the foundation for all subsequent cosmic flow studies. The WMAP satellite, launched in 2001, refined the measurement further and provided crucial validation of the kinematic interpretation. Planck, launched in 2009 by the European Space Agency, provided the definitive result: 620 plus or minus 15 kilometers per second in the direction of the constellation Crater, near the boundary with Leo. The equation that anchors this measurement is direct. Delta T over T is approximately V over C. The fractional temperature difference in the CMB dipole is approximately equal to the observer's speed divided by the speed of light. Planck measures delta T over T. The speed of light is known. The local group velocity follows: 620 kilometers per second, roughly 0.207% of the speed of light, a number we can state with precision, the direction we can map. What remains contested, even now, is the question of what produces that motion, which structures in the surrounding cosmic web bear responsibility, and how much of the budget belongs to pulling versus pushing. Think about that for a moment. We know our speed to within 15 kilometers per second. We know our direction to within a few degrees. What we are still working to determine is why we are moving in that direction at all. To understand the answer, we need to understand a concept that underpins the entire field: peculiar velocity. In a perfectly uniform expanding universe, every galaxy would recede from every other galaxy at a rate proportional to the distance between them. This defines the Hubble flow, the smooth, isotropic expansion described by the equation V sub h equals h naught times d. In this equation, V sub h represents the recession velocity due to expansion alone, h naught denotes the Hubble constant, the current expansion rate, and d marks the proper distance between observer and object. If the universe were perfectly homogeneous, this single equation would describe all motion. Every galaxy receding, every distance growing, every velocity predictable from distance alone. The universe is not perfectly homogeneous. It contains filaments, walls, clusters, superclusters, and voids, the structures collectively known as the cosmic web. These density variations produce gravitational potential gradients that accelerate galaxies on top of the Hubble expansion. The additional velocity, the deviation from the smooth Hubble flow, carries a specific name: peculiar velocity. The operational definition reduces to a subtraction. Vpec is approximately Cz minus h naught d. The peculiar velocity equals the observed recession velocity, approximated by the redshift z multiplied by the speed of light, minus the expected recession velocity from expansion, the Hubble constant times the independently measured distance. Measure the redshift. Measure the distance using some method that does not depend on redshift. A Tully-Fisher relation for spirals, a fundamental plane relation for ellipticals, a type 1a supernova, a tip of the red giant branch measurement. Subtract one from the other. What remains is the peculiar velocity. The Tully-Fisher relation, published in 1977 by R. Brent Tully and J. Richard Fisher, connects the rotational velocity of a spiral galaxy, measured from the width of its 21-centimeter neutral hydrogen emission line to its intrinsic luminosity. Faster rotating spirals carry greater luminosity. Measure the rotation speed from the spectral line width, infer the true luminosity, compare that to the observed brightness, and the distance follows from the inverse square law. The method is elegant, yet imperfect. Scatter in the relation introduces distance uncertainties of roughly 15 to 20% per galaxy. Group averaging, combining multiple galaxies known to sit at the same distance, reduces the scatter, and that is precisely why Cosmicflows catalogues group galaxies before constructing flow maps. The fundamental plane relation achieves something similar for elliptical galaxies, using three observable properties: effective radius, surface brightness, and velocity dispersion to infer distance. Type 1a supernovae, the explosion of white dwarf stars in binary systems, provide standardizable candles whose peak luminosities can be calibrated to yield distances across hundreds of megaparsecs. The tip of the red giant branch method relies on the known luminosity of old low-mass stars at a specific phase in their life cycle to calibrate distances to nearby galaxies. Each method carries its own systematic biases. Each covers a different distance range. Cosmicflows 4 employs 8 such methods, cross-calibrated against each other, to construct its catalogue of 55,877 galaxy distances. This is where the Cosmicflows program becomes central to the story. R. Brent Tully, working from the University of Hawaii, has spent decades assembling distance catalogues. The scope of this effort deserves a pause. Each galaxy distance in the catalogue represents hours of telescope time, spectroscopic observations to measure line widths, photometric observations to measure luminosities, careful calibration against known standards, correction for dust extinction and other systematic effects. The Cosmicflows compilations gather galaxy distances measured by multiple independent methods, cross-calibrate them, group galaxies to reduce noise, and produce the raw material from which velocity fields can be reconstructed. Cosmicflows 2, published in the years leading to the 2017 Dipole Repeller discovery, contained thousands of galaxy distances. Cosmicflows 4, published in 2023, compiles distances for 55,877 galaxies, grouped into 38,065 groups using 8 distance methodologies. Each generation of the catalogue extends the reach and density of the map. The grouping step carries particular importance for peculiar velocity work. Individual galaxy distances bear large fractional uncertainties, often 15 to 20%. Galaxies in a gravitationally bound group, though, all sit at approximately the same distance. By averaging the distance estimates for multiple galaxies in the same group, the uncertainty on the group distance drops by roughly the square root of the number of members. A group of 9 galaxies, for instance, would yield a distance estimate roughly 3 times more precise than any individual member. The 38,065 groups in Cosmicflows 4 represent this noise reduction step applied systematically across the catalogue. Tens of thousands of groups, each with a distance estimate cleaner than the individual galaxies that compose it. The distances themselves carry uncertainty. They depend on calibration chains, on assumed relationships between observable properties and true distances, on corrections for selection effects and non-Gaussian error distributions. One of the most persistent sources of systematic error goes by the name Malmquist bias, a well-documented selection effect in which intrinsically brighter objects are preferentially detected at greater distances, creating spurious inflows or outflows in the inferred velocity field if left uncorrected. Modern cosmic flows analyses apply explicit bias handling procedures, including a technique called bias Gaussianization correction, which transforms the log-normal-like distance error distributions toward normal ones before reconstruction. The corrections matter. The raw data arrives noisy, heterogeneous, and drawn from instruments spanning decades of astronomical surveys. What emerges from it is not a photograph of cosmic motion. It is a statistical inference constrained by data and shaped by priors. This is the part that stays with me, not because it is exciting, but because it serves as a reminder of how indirect these measurements are. We cannot watch galaxies move. We cannot point a camera at the cosmic web and record its flows. We measure distances and redshifts, one galaxy at a time, across catalogues of tens of thousands of objects, and then we reconstruct the velocity field from what is, fundamentally, a collection of subtractions. From those subtractions, a picture emerges, and the picture has held consistent for decades, even as the details sharpen and the debates intensify. For most of the late 20th century, the dominant framework for explaining the local group's motion centered on attraction. Somewhere in the direction of the constellations Centaurus and Norma, a massive concentration of matter appeared to be pulling us toward it. In the late 1980s, this region became known as the Great Attractor, a name that captured the imagination but also slightly misrepresented the physics. The Great Attractor is not a single object. It is a region of enhanced galaxy density centered near the Hydra Centaurus Supercluster complex, roughly 150 to 250 million light-years away, depending on which components are included. Early studies suggested the Great Attractor could account for a large fraction of the local group's peculiar velocity. As surveys extended to greater distances, though, a problem emerged. The Great Attractor region by itself could not account for all of the observed motion. Something more distant was needed. The residual velocity, the part left over after subtracting the Great Attractor's estimated contribution, pointed further out toward a region that surveys were only beginning to map in detail. The history of this discovery offers a lesson in how cosmological understanding evolves. In the late 1980s, the Seven Samurai, a group of 7 astronomers, including Alan Dressler, Sandra Faber, and Donald Lyndon Bell, published their analysis of galaxy distances and velocities that first identified the large-scale coherent flow toward the Centaurus region. Their work demonstrated that the flow extended far beyond what nearby clusters could explain. The term Great Attractor entered the lexicon. The Great Attractor, as a concept, turned out to be a placeholder for a more complex reality, a series of overlapping gravitational influences at different distances, with the closest contributions coming from Hydra Centaurus, and the more distant contributions from structures that would not be fully characterized for another 2 decades. That something turned out to be the Shapley Supercluster, the most massive concentration of galaxies in the nearby universe, located at a redshift range of approximately 0.04 to 0.055, corresponding to a distance of roughly 200 megaparsecs or about 652 million light-years, using a Hubble constant of 75 kilometers per second per megaparsec. The Shapley Supercluster is enormous. It contains multiple rich galaxy clusters, including Abell 3558 and Abell 3556, packed into a region dense enough to generate a measurable gravitational influence across hundreds of millions of light-years. Harlow Shapley first identified the Shapley concentration in the 1930s during his surveys of the southern sky, though the full extent and significance of the overdensity would not become clear until redshift surveys mapped it in 3 dimensions decades later. Michael Drinkwater and collaborators published detailed studies of the Shapley region's structure, finding a complex arrangement of interacting clusters, infalling groups, and connecting filaments concentrated within a relatively compact volume. The mass of the Shapley region resists precise estimation because it depends on how the boundaries are defined and how much intercluster matter is included. Yet it represents one of the densest concentrations of matter within roughly 1 billion light-years of the Milky Way. The significance of the Shapley concentration for the local group's motion lies in the reach of its gravitational influence. At 652 million light-years, light from the Shapley region has been traveling since before the most distant ancestors of modern mammals appeared on Earth. The gravitational field it generates has shaped flows across that entire distance for billions of years, contributing a persistent, slow pull on everything in its direction, including the local group, the Virgo cluster, and the entire Laniakea supercluster. Dale Kochevsky and Harold Eberling, working with X-ray selected galaxy cluster samples, published analyses quantifying the relative contributions to the local group's peculiar velocity. Their cluster dipole analysis attributed approximately 44% of the local group's motion to infall into the Great Attractor region, and 56% to large-scale flow from overdensities at distances of 130 to 180 H inverse megaparsecs, with the Shapley supercluster as a major single contributor beyond 130 H inverse megaparsecs. Other estimates placed Shapley's contribution at up to 25% of the total local group peculiar velocity, with the exact figure depending heavily on how much mass between clusters was included and how the boundaries of the supercluster were defined. The picture, then, was one of gravitational attraction. We are falling toward dense regions. The Great Attractor pulls from a moderate distance. Shapley pulls from further away. The velocities add. The direction aligns roughly with the observed CMB dipole. Case closed. Or so it seemed. The problem was that the accounting never quite balanced. The pull side of the ledger, even with Shapley included, left residuals. The direction came close but not exact. The amplitude appeared plausible but not fully convergent. Something was missing from the budget. In 2007, R. Brent Tully and collaborators published an analysis that introduced a different kind of contribution. They decomposed the local group's motion into 3 approximately orthogonal components. The first, with an amplitude of 259 kilometers per second, roughly 580,000 miles per hour, was attributed to motion away from the local void, a nearby underdense region adjacent to our position in the cosmic web. The second component, 185 kilometers per second, or about 414,000 miles per hour, was associated with the Virgo region. The third, 455 kilometers per second, pointed toward the Centaurus direction and captured the larger scale flow. The critical insight lay in the first component: motion away from the local void, not toward a mass concentration, away from an absence. This was not new physics. It was standard gravitational dynamics viewed from a different angle. In a universe where density lacks uniformity, peculiar velocities trace gradients of the gravitational potential. Overdensities produce convergent flows where matter falls toward them. Underdensities produce divergent flows where matter moves away from them toward the surrounding denser regions. The effect operates symmetrically in the equations but asymmetrically in the narrative. For decades, cosmology had emphasized the attractors. Tully's decomposition placed the voids back into the accounting. The physics finds its description in the Poisson equation in its cosmological form. Laplacian phi is proportional to delta. The Laplacian of the peculiar gravitational potential is proportional to the overdensity. Where delta is positive, where matter is denser than the cosmic mean, the potential configuration produces inward peculiar accelerations. Where delta is negative, where matter is less dense than the cosmic mean, the potential configuration produces outward peculiar accelerations. The void does not push in the sense of exerting a force. The void is a region where the inward gravitational acceleration falls weaker than it would be if the region contained the average density. The net effect, after subtracting the uniform expansion, is a peculiar acceleration directed away from the void interior and toward the surrounding denser structures. Rian van der Weijgaert, in influential reviews of void dynamics, described this precisely. Underdensities correspond to regions of weaker gravity. Matter within and near a void experiences a net peculiar acceleration outward toward the walls and filaments that surround it. The void interior empties further. The boundaries compress. The void expands relative to the cosmic mean. None of this requires new forces, exotic matter, or modifications to general relativity. The mechanism is standard gravitational instability in a universe with density contrasts. The process operates cumulatively and self-reinforces, though not through any feedback mechanism, simply through the mathematics of gravitational collapse in reverse. As matter flows outward from the void interior toward surrounding overdensities, the void becomes even more underdense. The density contrast deepens. The outward peculiar acceleration strengthens. Over billions of years, what may have begun as a modest underdensity in the early universe, a region perhaps 10 or 20% less dense than the cosmic mean, can develop into a pronounced void surrounded by compressed walls and filaments that collected the evacuated matter. The cosmic web is not static. It represents the cumulative result of 13.8 billion years of gravitational development, with overdensities growing denser and underdensities growing emptier according to the same set of equations. The timescales involved resist easy appreciation. The density contrasts visible in the cosmic microwave background, the tiny temperature fluctuations measured by Planck at the level of 1 part in 100,000 represent the seeds from which all present-day structure developed. The Shapley Supercluster, the local void, the Dipole Repeller, all of these descended from those primordial fluctuations, amplified over cosmic time by the relentless accumulation of gravitational effects. The void that pushes us today was, 13.8 billion years ago, a slightly underdense patch in a nearly uniform sea of matter and radiation. Nothing more. The physics did the rest. Before we continue, consider what this means. The same physics that makes a supercluster attract also makes a void repel in the peculiar velocity sense. the same equations, the same gravitational dynamics. The difference lies only in the sign of the density contrast. Positive delta pulls, negative delta pushes. The motion budget of our cosmic neighborhood carries 2 columns, and for decades we had been reading only one. This brings us to the Dipole Repeller and the 2017 paper that placed both columns side by side for the first time in a single velocity field reconstruction. Yehuda Hoffman, Daniel Pomerade, R. Brent Tully, and Hélène Courtois, the team behind some of the largest advances in cosmic flow mapping, applied a Wiener filter reconstruction to the Cosmicflows 2 distance catalog. The Wiener filter functions as a Bayesian linear estimator. It takes noisy, incomplete data, the peculiar velocities inferred from Cosmicflows 2, and combines them with a prior model, in this case the lambda CDM cosmological model, to produce a statistically optimal reconstruction of the underlying density and velocity fields. Where data are dense, the reconstruction follows the data. Where data are sparse or absent, the reconstruction relaxes toward the prior, toward the mean, toward homogeneity. The reconstruction produced a 3-dimensional map of the local velocity field, capturing the flows, the convergences, the divergences. The method deserves closer examination, because the Dipole Repeller is not an object found by pointing a telescope at a particular patch of sky. It is a feature extracted from a statistical reconstruction, and understanding what that means is necessary for evaluating the evidence. The Wiener filter operates by minimizing the expected mean-squared error between the reconstructed field and the true underlying field. In practice, it takes the observed peculiar velocities, measured at the positions of the Cosmicflows 2 galaxies, and uses them, together with the assumed statistical properties of the lambda CDM density field, to estimate the velocity and density at every point in the volume. The output is a smooth, continuous field that best matches the data given the prior. Constrained realizations, random samples drawn from the distribution of fields consistent with both the data and the prior, provide estimates of the uncertainty. Run the reconstruction many times with different random seeds, and the spread of results reveals how reliable each feature is. The velocity shear tensor, constructed from the spatial derivatives of the reconstructed velocity field, adds another layer of information. Its eigenvalues and eigenvectors classify the local geometry of the cosmic web, distinguishing regions of compression, such as clusters and filaments, from regions of expansion, such as sheets and voids. The V-web classification, developed by Hoffman and collaborators, uses the velocity shear tensor to partition the cosmic web into dynamically defined environments. In the 2017 paper, the attractor emerges through the shear tensor's alignment with the Shapley direction, while the repeller emerges through the bulk flow dipole's anti-alignment with the void direction. Attractor and repeller map onto different multipole moments of the velocity field, the quadrupole and the dipole, respectively, and their relative dominance varies with distance from the observer. From this map, the team identified the dominant structures shaping the local group's motion. On the pull side, the Shapley Supercluster emerged as the primary attractor, dominating the shear tensor and quadrupole component of the velocity field out to roughly 7,000 kilometers per second, approximately 90 to 117 megaparsecs, or 295 to 380 million light-years. On the push side, something new appeared. A region from which reconstructed streamlines diverged, located roughly opposite to Shapley in the reconstructed flow geometry. The team applied a technique they called anti-flow. reversing the direction of the velocity field, which transformed the repeller into a convergence point, making its position identifiable. They named it the Dipole Repeller. The Dipole Repeller dominated the bulk flow dipole, the volume average peculiar velocity of the local region, out to approximately 16,000 plus or minus 4,500 kilometers per second. In physical distance, that corresponds to roughly 160 plus or minus 45 megaparsecs per h, or approximately 685 to 850 million light-years for plausible values of the Hubble parameter. The alignment proved striking. The cosine alignment between the bulk flow direction and the anti-repeller direction reached mu sub bulk approximately negative 0.96 plus or minus 0.04 around that scale. Negative 0.96 on a scale, where negative 1 means perfect anti-alignment. The bulk flow points almost exactly away from the repeller. The paper presented this as a repeller-attractor pair. The dipole repeller shaping the dipole moment of the flow, and the Shapley attractor shaping the quadrupole and shear. Two structures, two contributions, two halves of a single accounting ledger for the local group's observed peculiar velocity. A key methodological note from the same paper, and one that matters for understanding what the reconstruction shows. The plotted streamlines serve as a visualization tool for the vector field. They do not represent trajectories. The map captures a snapshot of the reconstructed velocity field at one moment. It shows the instantaneous flow pattern, not the historical paths of galaxies over billions of years. This distinction carries real weight. It marks the difference between a wind map and a flight path. The dipole repeller reconstruction tells us about the current field structure. It does not tell us where galaxies came from or where they will end up. What would you conclude from this evidence? A void identified by the divergence of reconstructed flow lines positioned opposite the most massive known attractor, anti-aligned with the bulk flow to within a few percent. The direction matches, the scale matches, the physics is standard. And the implication is that for decades, the missing contribution to our motion, the part that the attractors alone could not account for, was, in part, the push of absence. This is the part of the investigation that requires precision about language. The dipole repeller is not a new fundamental force. It is not anti-gravity. It is not negative mass. It is not a repulsive field generated by exotic particles. In the Hoffman team's reconstruction, the dipole repeller is a feature in the velocity potential, a region associated with a void in the galaxy distribution where the reconstructed peculiar velocity field diverges. The repulsion operates effectively, not fundamentally. It results from a mass deficit relative to the cosmic mean. The surrounding denser regions exert stronger gravitational attraction than the void interior does. The net peculiar acceleration points outward. In co-moving coordinates, the reference frame that factors out the uniform expansion, this can be described as the void applying a repulsive influence. Hoffman and colleagues use precisely that language, noting that in co-moving coordinates, underdensities apply a repulsive force and overdensities an attractive one. The language holds defensible ground but requires care. Repulsive gravity misleads because gravity, in general relativity, always attracts between masses. Effective repulsion in the peculiar velocity field captures the physics accurately but resists smooth-spoken delivery in a documentary. The compromise, the void pushes, with the understanding that the push is a differential effect, weaker inward gravity relative to the cosmic mean. not an outward force in the traditional sense. The linearized continuity equation formalizes the connection between density and flow. Partial delta by partial t plus 1 over a times the divergence of v equals 0. The rate of change of the overdensity plus 1 over the scale factor times the divergence of the peculiar velocity field equals 0. This expresses conservation of mass in the linear regime. Where the overdensity is negative, where the density falls below the cosmic mean, the divergence of the velocity field turns positive. Positive divergence means outflow. Voids correspond to outflowing regions. The equation does not assign agency. It describes a relationship between density contrast and velocity divergence, and the relationship holds exact in the linear approximation. The linear growth factor relation adds the time dimension. Delta of x and t equals d plus of t times delta naught of x. The overdensity at position x and time t equals the linear growth factor at time t multiplied by the initial overdensity at position x. Structures grow over time. Overdensities become denser, underdensities become emptier. The growth factor d plus of t depends on the cosmological parameters, the matter density, the dark energy density, the expansion history. The growth rate, f, defined as d log d by d log a, the logarithmic derivative of the growth factor with respect to the scale factor, quantifies how quickly structures grow relative to the expansion. Many claims about anomalies and new physics reduce, ultimately, to whether the measured growth rate matches the predicted one. Peculiar velocity surveys, including Cosmicflows, measure a combination called f sigma 8, the growth rate multiplied by the amplitude of density fluctuations, a crucial parameter for testing structure formation models. Courtois and collaborators, in their 2023 CF4 public reconstruction, report F sigma 8, approximately 0.38 plus or minus 0.04 from ungrouped data. This number connects the motion we measure to the rate at which the cosmic web assembles. The growth rate definition is clean. F equals d log d by d log a. 5 symbols. One concept: how fast is structure forming? The answer determines how strong the peculiar velocities should be, how large the bulk flows should be, and whether what we observe matches what the standard model predicts. If the match holds, the Dipole Repeller and the Shapley Attractor are features of a universe behaving as expected. If it does not, the features might serve as signposts of something we have not yet accounted for. We are now deep enough into the evidence to examine what changed between 2017 and 2025, and the answer comes down to data volume and inference diversity. The 2017 Dipole Repeller paper relied on Cosmicflows 2, a smaller, earlier distance compilation. The reconstruction depended on Wiener filtering with a lambda CDM prior. The repeller was identified in the resulting velocity field, and robustness checks were performed by truncating the data to smaller radii. Hoffman and colleagues argued that the repeller's direction held steady, though they acknowledged that the amplitude comparison between attractor and repeller regions was less direct because sampling differed between the two, with the repeller lying in a direction where galaxy survey coverage is sparser. By 2023, the landscape had shifted. Cosmicflows 4 brought 55,877 galaxy distances across 8 methodologies. Multiple independent reconstruction pipelines now operate on CF4 class data. Wiener filter and constrained realization approaches, incorporating explicit bias, Gaussianization correction, reconstruct the linear density and velocity fields. Hamiltonian Monte Carlo methods, led by Aurélien Valade and collaborators, provide probabilistic reconstructions with different statistical properties. Direct bulk flow estimators with extensive mock testing offer independent checks on the flow amplitude and direction. Hoffman and collaborators, applying their updated Wiener filter with bias correction to CF4, found that the inferred bulk flow profile is somewhat atypical but not a decisive failure of the lambda CDM model. They also demonstrated an important and uncomfortable finding. The bulk flow profile depends significantly on which subsample of CF4 dominates at a given distance. Beyond approximately 120 H-inverse megaparsecs, the 6DF Galaxy Survey, a major CF4 component focused on the southern sky, drives a prominent hump in the reconstructed bulk flow. This subsample dominance means that claims about unexpectedly large flows at those distances are, in part, claims about the sky coverage and selection properties of a single survey contributing to the compilation. Richard Watkins and Hume Feldman, working with CF4 data and minimum variance bulk flow estimators, published analyses arguing that the bulk flow inferred at radii of 150 to 200 H-inverse megaparsecs carries a very low probability under lambda CDM parameters derived from the CMB. Taken at face value, this would suggest that the large-scale flows, driven by the same density contrasts that define the Dipole Repeller and the Shapley Attractor, exceed expected amplitudes. Other analyses urge caution. Andrew Whitford and collaborators emphasized that systematic differences between estimator choices can drive contradictory bulk flow claims. The same data, processed through different statistical machinery, yields different answers about how unusual the flows are. This does not represent a failure of the data. It reflects the nature of inference at the limits of measurement, where signal and noise overlap, where sky coverage remains uneven, and where the choice of how to weight observations can shift a result from somewhat atypical to highly unlikely and back again. Think about that. The same catalogue of galaxy distances, the same peculiar velocities derived from the same subtractions. Yet the statistical question, is this flow consistent with our cosmological model, yields different answers depending on how you ask it. This is the forensic reality of modern observational cosmology. The evidence does not speak for itself. It speaks through the estimators, the priors, the corrections, and the mock catalogues used to validate them. The mock catalogues deserve mention because they represent one of the most important yet least visible components of the analysis. To determine whether an observed bulk flow is unusual, you need to know what typical bulk flows look like in a universe that matches the standard model. This requires generating hundreds or thousands of simulated universes, mock catalogues that reproduce the statistical properties of lambda CDM, including the survey geometry, the selection effects, the distance errors, and the grouping procedures of the real data. The observed flow is then compared to the distribution of flows in the mocks. If the observed flow falls in the tail of the mock distribution, beyond the 95th or 99th percentile, it is flagged as anomalous. The mock catalogues themselves, though, carry assumptions about the cosmological parameters, the initial conditions, and the details of the survey model. Change those assumptions, and the mock distribution shifts, and the percentile of the observed flow shifts with it. Watkins and Feldman argue that their mock comparison places the CF4 bulk flow in the extreme tail below the 1% level of the lambda CDM distribution. Hoffman's analysis, using different reconstruction techniques and different treatment of subsamples, characterizes the same underlying data as somewhat atypical but within a range that does not compel rejection of the standard model. The difference does not reduce to who is right and who is wrong. It reveals how sensitive the answer is to the details of the analysis pipeline, a sensitivity that, at the current data quality, remains unresolved. In 2025, the Cosmicflows program took another step. Hélène Courtois and collaborators published CF4++, an update that incorporates early peculiar velocity datasets from 3 new sources: Wallaby, the Widefield ASCAP L-band Legacy All-Sky Blind Survey conducted on the Australian Square Kilometre Array Pathfinder; FAST, the 500-metre aperture spherical telescope in China, opened to the global community in 2021; and DESI, the dark energy spectroscopic instrument mounted on the Mayol 4-metre telescope at Kitt Peak National Observatory, using 5,000 robotic fiber positioners to obtain spectra at unprecedented speed. The Australian Square Kilometre Array Pathfinder became fully operational in 2019. Wallaby, its flagship neutral hydrogen survey, released its Pilot Data Release 1 in November 2022 and Pilot Data Release 2 in September 2024. The survey detects neutral hydrogen emission from galaxies across the southern sky, providing the raw material for Tully-Fisher distance measurements. FAST, with its 500-metre diameter illuminated aperture, stands as the most sensitive single-dish radio telescope operating today. Its neutral hydrogen surveys contribute peculiar velocity data from a complementary region of the sky. Together with DESI's spectroscopic capabilities, these instruments represent a qualitative expansion in the data available for cosmic flow mapping, spanning new wavelength regimes, new sky coverage, and new distance indicators feeding into the same reconstruction framework. CF4++ incorporates sample counts of 655, 4,796, and 4,191 peculiar velocity measurements from these surveys, respectively. The resulting reconstruction reports a bulk flow of 315 plus or minus 40 kilometers per second at 150 megaparsecs per hour. Courtois and collaborators state explicitly that dynamical homogeneity, the scale at which bulk flows, should diminish to near zero if the universe is statistically homogeneous, is not reached at 200 to 300 megaparsecs per hour in their analysis. That last finding carries significance. The standard cosmological model predicts that on sufficiently large scales, peculiar velocities should average out. The bulk flow should converge towards zero. If it does not, if coherent flows persist at scales of 200 to 300 megaparsecs, the implication falls into one of 2 categories. Either structures at those scales are larger or more pronounced than standard simulations predict, or systematic effects in the data or analysis are inflating the inferred flows. The debate remains unsettled. The data accumulates. The answer has not yet come clear. 200 to 300 megaparsecs placed in perspective. 1 megaparsec spans approximately 3.26 million light-years. 300 megaparsecs stretches to roughly 1 billion light-years. The claim that dynamical homogeneity has not been reached at that scale means that the peculiar velocities of galaxies, the deviations from smooth expansion, remain coherent across a volume roughly 1 billion light-years in extent. The structures driving those coherent motions, the attractors pulling and the voids pushing, must themselves span comparable scales, or at least generate gravitational fields that extend that far. This connects to a deeper question about the cosmological principle, the foundational assumption that the universe is statistically homogeneous and isotropic on sufficiently large scales. The assumption does not require the universe to be perfectly smooth. It requires that the statistical properties of the density field, its average, its variance, its correlation structure, do not depend on where you measure them. Coherent flows at 200 to 300 megaparsecs do not necessarily violate this principle, but they constrain where the transition to homogeneity occurs and how pronounced the remaining structures can be at those scales. If future surveys with better sky coverage and more precise distance measurements confirm that the bulk flow persists at these scales, the implications for the standard model would be serious, not necessarily fatal, but requiring either an explanation within the model, a rare but allowable realization of the initial conditions, or a modification of the model itself. This brings us to an aspect of the investigation that the 2017 paper could not fully address, and that the 2023 to 2025 updates have begun to probe: the evolving map of basins of attraction in the local universe. In 2014, R. Brent Tully, Hélène Courtois, Yehuda Hoffman, and Daniel Pomarade published a landmark paper defining the Laniakea Supercluster, the structure within which the Milky Way resides. Laniakea was defined not by galaxy density alone, but by the topology of the peculiar velocity field. Using watershed surfaces, boundaries where flow lines diverge rather than converge, they carved the local universe into basins of attraction, each centered on a convergence point in the velocity field. Laniakea emerged as a single basin, stretching roughly 160 megaparsecs across, encompassing approximately 100,000 galaxies. The name, chosen by Tully, comes from the Hawaiian words Lani, meaning heaven, and Akea, meaning immeasurable, a fitting description for a structure so large that light takes over 500 million years to cross it. In that 2014 paper, the team demonstrated that the Milky Way sits not at the center of Laniakea, but near its outer edge, close to the boundary with an adjacent basin. Our position in the cosmic web is peripheral, not central, a fact that carries no significance beyond geometry, but one that reinforces the theme of scale running through this entire investigation. The boundaries of Laniakea are not walls or edges in the physical sense. They are surfaces in the velocity field where the flow direction reverses, where galaxies on one side flow toward the Laniakea attractor and galaxies on the other side flow toward a different basin's attractor. Cross the boundary and the local flow changes direction. The boundary itself is a mathematical construct derived from the reconstructed field, not a physical barrier. It defines, though, in a dynamically meaningful way, the extent of the structure we inhabit. The watershed concept carries power because it defines structure by dynamics, not by density. A supercluster in this framework is a region from which all internal flows converge toward a single attractor. Its boundary marks where the flows begin to diverge, where one basin ends and another begins. The Dipole Repeller in this framework sits near or beyond Laniakea's boundary, in a direction where flow lines diverge rather than converge. Aurélien Valade, working with CF4 data and Hamiltonian Monte Carlo reconstructions, published updated basin of attraction identifications in 2024. The Hamiltonian Monte Carlo approach differs from the Wiener filter in important ways. Where the Wiener filter produces a single best estimate field plus constrained realizations for uncertainty, the Hamiltonian Monte Carlo method samples the full posterior distribution of density and velocity fields consistent with the data, exploring a wider range of possibilities and providing a more complete picture of the uncertainty landscape. The results prove interesting and, in some ways, destabilizing. With the larger CF4 dataset, the analysis suggests that Laniakea may not be an independent basin at all. Laniakea may instead be part of a larger Shapley basin, a much more extensive convergence region centered on the Shapley Supercluster. The boundaries between basins shift with the data. What appeared to be a distinct supercluster in the CF2 era may, with more galaxies and better distance measurements, dissolve into a subdivision of something larger. The implications of this for the dipole repeller are indirect, but worth noting. If Laniakea forms part of a larger Shapley basin, then the flow topology of the local universe is simpler than the CF2 era picture suggested. A single dominant attractor in Shapley and a single dominant repeller in the Dipole Repeller, rather than multiple competing basins. The basic push-pull framework survives, but the scale of the structures involved may exceed original characterizations. The investigation does not change in kind. It changes in scope. Alexandre Dupuy, working with CF4 velocity fields to delineate superclusters as watersheds, formalized the size comparisons between observed watershed superclusters and those found in lambda CDM simulations. The work connects directly to the question of whether observed structures are consistent with the standard model or whether they are, in some quantifiable sense, larger or more coherent than simulations predict. The answer, as with much in this field, depends on the details: the reconstruction method, the simulation resolution, the definition of structure. Science can describe what happens and how it happens. The question of why anything exists at all, why there is something rather than nothing, why these density contrasts and not others, why this particular arrangement of voids and superclusters in this particular region of the observable universe sits beyond the reach of telescopes and equations. The Cosmicflows reconstructions can map the field. They cannot explain why the field takes this particular form. Cosmological models treat the initial conditions statistically, as one realization drawn from an ensemble of possibilities consistent with the physics. The specific pattern of the local cosmic web, the dipole repeller here, Shapley there, the local void adjacent, cannot be derived from first principles. The map records the arrangement. The theory explains the dynamics. The arrangement itself is a given. Now let us examine the counter-narrative. Every forensic investigation requires this. The systematic testing of the evidence against alternative interpretations, the identification of weaknesses, the acknowledgement of what remains uncertain. The dipole repeller reconstruction carries several key assumptions. The first holds that the flow field is well approximated by linear theory on the scales of interest. The Wiener filter relies on this, reconstructing the linear density and velocity fields using a lambda CDM prior and assuming that the relationship between density contrast and velocity is described by the linearized equations. On scales of hundreds of megaparsecs, this approximation is generally considered valid. On smaller scales, nonlinear effects matter. The reconstruction operates in a regime where the linear approximation holds reasonable but not exact. The second assumption involves the lambda CDM prior itself. The Wiener filter is explicitly Bayesian, and it tends toward the prior where data are weak. In regions of sparse galaxy coverage, which includes the direction of the dipole repeller where surveys run thinner, the reconstruction relaxes toward homogeneity, toward the cosmic mean. The implication is subtle but important. The dipole repeller, as identified in the reconstruction, may actually underestimate the true underdensity because the prior pulls the solution toward uniformity where data are sparse. Alternatively, the feature could be an artifact of the data edge, a structure that appears because the reconstruction must smoothly transition from data-constrained regions to prior-dominated regions, and the transition can create apparent features in the field. Hoffman and colleagues explicitly considered this. The attractor and repeller both lie near the edge of the CF2 data coverage. They performed robustness checks by truncating the data to smaller radii and confirmed that the directional alignment held stable. The direction of the repeller remained consistent. Its amplitude, though, proved harder to pin down because the repeller region contains fundamentally less data than the attractor region. Shapley is a dense concentration of galaxies, offering many distance measurements. The dipole repeller is, by definition, underdense, containing fewer galaxies and fewer distance measurements. The third assumption concerns distance indicator systematics. Cosmicflows catalogs combine distances from multiple methods: Tully-Fisher relations for spiral galaxies, fundamental plane relations for ellipticals, Type 1a supernovae, surface brightness fluctuations, tip of the red giant branch measurements, and others. Each method carries its own calibration uncertainties, selection effects, and systematic biases. The cross-calibration between methods proceeds carefully but imperfectly. Zero-point offsets between methods, small systematic differences in the distance scale as calibrated by each technique, can introduce spurious flows if uncorrected, because a zero-point error in one method translates directly into a false peculiar velocity for every galaxy measured with that method. Malmquist bias, the preferential detection of intrinsically brighter objects at greater distances, can mimic or distort inferred flows if uncorrected. The effect operates subtly but pervasively. Consider a volume of space at a given distance. The galaxies within it span a range of intrinsic luminosities. A flux-limited survey, one that detects all objects above a certain brightness threshold, will preferentially select the brighter end of this distribution. Because the Tully-Fisher and fundamental plane relations possess intrinsic scatter, the brighter galaxies are, on average, those that scattered to the luminous side of the relation. Their distances will be systematically underestimated. The relation predicts a lower luminosity than they actually have, which makes them appear closer than they are. This systematic distance underestimate creates a spurious inward peculiar velocity. Multiply this across thousands of galaxies, and it can introduce coherent false flows into the reconstructed field. The CF4 era analyses apply explicit corrections, including the bias Gaussianization correction developed by Hoffman and collaborators, yet the corrections themselves depend on assumptions about the error distributions. The log-normal character of distance errors, distances cannot be negative, and the fractional errors maintain rough symmetry in logarithmic space, means that standard Gaussian methods can underperform. The BGC technique transforms the errors toward Gaussianity before the Wiener filter reconstruction, reducing one known source of bias. Whether it eliminates the bias entirely or only reduces it to a level below the current noise floor remains an open question that future data and simulations will help resolve. The fourth factor is sky incompleteness, the zone of avoidance, The region near the plane of the Milky Way, where dust and stars obscure our view of extragalactic objects, creates a band of missing data across the sky. The zone of avoidance covers roughly 20% of the sky at optical wavelengths, narrowing at infrared and radio wavelengths but never disappearing entirely. Structures hidden behind the galactic plane cannot be mapped directly. They must be inferred from the surrounding data and the prior, or they simply remain absent from the reconstruction. If a major overdensity sits in the zone of avoidance, its gravitational pull would be missing from the accounting, potentially shifting the inferred balance between push and pull. This is not a hypothetical concern. The Great Attractor region itself lies partially behind the zone of avoidance, and that is precisely why its characterization took so long and remains incomplete. Near-infrared surveys like 2MASS have partially penetrated the zone, revealing galaxy concentrations that optical surveys missed entirely. Radio surveys, particularly 21-centimeter hydrogen surveys, can detect gas-rich galaxies through the galactic plane. Coverage remains uneven, though, and structures in the most heavily obscured regions stay poorly constrained. A 2025 study examined zone of avoidance effects specifically in the context of Cosmicflows reconstructions, highlighting that hidden structures can materially change the inferred flow drivers. The Dipole Repeller direction, it should be noted, does not lie behind the zone of avoidance. It remains accessible to surveys. The completeness of the overall map, including the regions that contribute to the pull side of the ledger, depends on how well the zone of avoidance is handled. Missing pull sources would make the repeller appear relatively more important in the accounting. Excess pull sources hidden behind the galactic plane could reduce the inferred repeller contribution. Noam Libeskind and collaborators working at the interface of cosmological simulations and reconstructions have explored how these limitations affect the reliability of inferred structures. The conclusion holds consistent across studies. The broad features of the velocity field, the direction and approximate amplitude of the bulk flow, the positions of the largest attractors and repellers are stable across reasonable variations in methodology and data. The fine details, the exact amplitude of the repeller's contribution, the precise boundary between basins, the subsample dependence of the bulk flow at large distances, remain sensitive to the choices made in reconstruction. I return to this point often, not for comfort, for clarity. The Dipole Repeller is not a speculation. It is a feature of a well-characterized reconstruction, identified using standard techniques, consistent with known physics, and confirmed in direction by multiple independent analyses. Its precise amplitude, its exact contribution to the local group's motion budget, and its stability under future data improvements all remain open questions. The map is not a photograph. It is a best-fit field etched out of noisy distance ladders and statistical priors. The bulk flow debate amplifies these concerns. Richard Watkins and Hume Feldman, using minimum variance estimators on CF4 data, argue that the inferred bulk flow at large radii is highly improbable under standard lambda CDM parameters. If correct, this would suggest that the structures driving cosmic flows, including the Dipole Repeller and the Shapley region, are either larger, deeper, or more coherent than the standard model predicts. The implication extends beyond the local velocity field to questions about the cosmological model itself. Andrew Whitford and collaborators counter that estimator-dependent biases and systematics can materially change bulk flow inferences. They advocate careful validation of estimator variance against mock catalogues before drawing cosmological conclusions. The message is clear. The same data, processed differently, tells different stories about whether the flows are anomalous. The tension sits as much in methodology as in the universe itself. Hoffman's own CF4 analysis adds nuance. The reconstructed bulk flow profile shows features, including a hump beyond 120 H-inverse megaparsecs, that are driven largely by one subsample, the 6DF Galaxy Survey. The 6DF contribution dominates the southern sky coverage at those distances. Remove it or change its weighting, and the profile changes. This does not constitute evidence of fraud or failure. It constitutes evidence that at the frontier of the data, where galaxy counts thin and sky coverage becomes uneven, the inferred field grows sensitive to the composition of the input catalog. The Dipole Repeller's influence at those distances is entangled with the survey properties of the instruments that measured it. What would you conclude from this? A reconstruction built on tens of thousands of galaxy distances, confirmed in direction but debated in amplitude, sensitive to subsamples at its outer edges with different statistical approaches yielding different assessments of its cosmological significance. The evidence file is thick. The verdict has not yet arrived. This brings us to a broader question, one that connects the Dipole Repeller to the frontiers of cosmological research. What can voids tell us about the physics of the universe? Cosmic voids are not just empty space, they are laboratories. Because voids are underdense, the matter within them is less gravitationally bound than matter in clusters or filaments. In modified gravity theories, models that alter general relativity on cosmological scales, the gravitational behavior in voids can differ from the standard prediction in measurable ways. Some classes of modified gravity models, including chameleon and F of R gravity theories, employ a mechanism called screening, in which the modification to gravity is suppressed in dense environments but expressed in underdense ones. Voids, by their nature, are the least screened regions of the universe. If gravity is modified, voids are where the modification should be most detectable. The predictions are specific. In certain chameleon-type models, voids are predicted to expand 20 to 30% faster than in standard general relativity in some regimes. Their sizes can reach approximately 10% larger. Their abundances, how many voids of a given size exist in a given volume, shift in calculable ways. These are not vague predictions. They are testable differences that surveys like DESI and the Vera Rubin Observatory's Legacy Survey of Space and Time are designed to probe. DESI, which began its main survey in 2021, employs 5,000 robotic fiber positioners on the Mayall 4-meter telescope at Kitt Peak to obtain spectra of tens of millions of galaxies and quasars. The spectroscopic precision allows three-dimensional mapping of the cosmic web at scales and depths that previous surveys could not achieve. Void identification in DESI data, finding the underdense regions, measuring their shapes, tracking their internal velocities, will provide some of the most stringent tests of gravity and dark energy available from current generation instruments. The Vera Rubin Observatory, under construction in Chile, will survey the southern sky with a 3.2 gigapixel camera, cataloging billions of galaxies and detecting transient events across half the sky. Its depth and coverage will enable void statistics at redshifts, where the effects of modified gravity or dynamical dark energy would be most pronounced. The ESA Euclid mission, launched in 2023, adds space-based photometric and spectroscopic surveys covering 15,000 square degrees of sky, designed specifically to constrain dark energy and test gravity through weak lensing, galaxy clustering, and, increasingly, void statistics, The convergence of these instruments on the same questions, how fast are voids expanding, how large are they, how abundant are they, do they match lambda CDM predictions, represents one of the most targeted observational programs in modern cosmology. The Dipole Repeller, as a specific and well-characterized void-associated feature, sits at the intersection of local cosmic flow studies and this broader program of fundamental physics tests. Alice Pisani, Nico Hamaus, and collaborators have developed void statistics as cosmological probes, using void abundances, shapes, and internal dynamics to constrain dark energy parameters and test gravity. The Alcock-Paczynski test, which uses the observed shapes of statistically isotropic objects to constrain cosmological geometry and expansion history, has been applied to stacked void profiles with promising results. Void redshift space distortions, the way void shapes appear distorted along the line of sight due to peculiar velocities within and around them, provide independent measurements of the growth rate F sigma 8. Void lensing, the gravitational lensing signal around voids, offers yet another probe. A 2024 analysis using BOSS DR12 voids reports void-derived constraints on S sub 8 and H naught that are compatible with the broader literature. The constraints do not by themselves demand new physics. They demonstrate, though, that the methodology has matured and that voids are becoming serious cosmological probes alongside the more traditional tools of galaxy clustering, CMB anisotropies, and Type 1a supernovae. The connection to the dipole repeller runs through the physics. The same dynamics that produce the void-driven outflows identified in the Cosmicflows reconstructions also produce the observational signatures that void cosmology aims to exploit. If the dipole repeller's associated void is large enough and deep enough, its expansion rate, its internal dynamics, and its influence on the surrounding flow field all become data points in the broader effort to test gravity and dark energy. The local void functions not just as a feature of our cosmic address. It serves as a potential laboratory for fundamental physics. Dynamical dark energy adds another dimension to the story. If the dark energy equation of state varies with redshift, if W of Z departs from exactly -1, then the growth of structure changes over time in ways that affect void statistics. Voids become larger or smaller, more abundant or less abundant, depending on the dark energy history. Current observational constraints from void statistics remain relatively broad, but they sharpen with each survey generation. The equation of state parameter W, defined as the ratio of pressure to energy density for dark energy, determines how the expansion accelerates and, through the growth factor, how structures, including voids, develop over cosmic time. The potential link between local void dynamics and the Hubble tension, the persistent disagreement between locally measured and CMB inferred values of the Hubble constant, has also been explored, though cautiously. The Hubble tension stands as one of the most discussed open problems in cosmology. Measurements using the cosmic distance ladder, Cepheid variables calibrating Type 1a supernovae, yield a Hubble constant of approximately 73 kilometers per second per megaparsec. The CMB measurement from Planck, calibrated through the standard cosmological model, yields approximately 67.4 kilometers per second per megaparsec. The discrepancy reaches statistical significance at roughly 5 sigma, and it has persisted across multiple independent measurement methods and teams. The KBC void hypothesis, named after Ryan Keenan and collaborators, proposes that a sufficiently large local underdensity, a supervoid surrounding our position in the cosmic web extending to roughly 300 megaparsecs, could bias locally inferred expansion rates upward. If we sit inside a region that is less dense than the cosmic mean, the local expansion rate would run faster than the global average, and distance ladder measurements sampling primarily the local universe would yield a higher Hubble constant than the CMB derived value, which reflects the global expansion history. The idea is physically plausible. The question centers on whether a void of the required size and depth is consistent with lambda CDM expectations. Some analyses argue that such a void is difficult to reconcile with lambda CDM expectations, that the probability of finding ourselves inside an underdensity large enough and deep enough to produce the observed Hubble tension drops very low in standard simulations. Others explicitly test local supervoid models against multiple datasets and find difficulties and degeneracies, where the void parameters needed to resolve the Hubble tension can conflict with other observations, including the bulk flow measurements and the CMB itself. The claim remains disputed and is best treated as an alternative hypothesis under active scrutiny, not a consensus explanation. The dipole repeller, as a void-associated feature in the reconstructed velocity field, is conceptually related but not identical. The dipole repeller characterizes the flow topology, while the KBC void hypothesis addresses the expansion rate. The two are connected through the underlying density field, but address different observational signatures. We can measure the distances, calculate the masses, map the structures. What set all of this in motion and why these laws, and not others, remains unanswered. The investigation carries one more dimension to examine, the question of the CMB dipole itself. The entire peculiar velocity framework assumes that the CMB dipole is kinematic, that it arises from our motion through the CMB rest frame and nothing else. If part of the dipole were intrinsic, if the CMB itself were anisotropic for reasons unrelated to our motion, then the velocity inferred from the dipole would be incorrect, and the entire flow reconstruction built upon it would require revision. This is not an academic concern. The CMB dipole serves as the single most important anchor in the peculiar velocity framework. Every flow map, every bulk flow estimate, every reconstruction of attractors and repellers is calibrated against it, either directly or indirectly. If the anchor shifts, the entire map shifts with it. The stakes run high enough that multiple independent tests have been conducted. The kinematic interpretation predicts a specific relationship. If the CMB dipole is caused by our motion, then distant objects, galaxies, quasars, radio sources should show a corresponding dipole in their number counts. Objects in the direction of our motion should appear slightly brighter and more numerous due to aberration and Doppler boosting, while objects in the opposite direction should appear fainter and fewer. The amplitude and direction of this number count dipole should match the CMB dipole within well-defined uncertainties. Analyses have examined this possibility and placed constraints. The kinematic interpretation of the CMB dipole retains strong support. The intrinsic contribution, if any, is small. The question has been raised with renewed intensity, though, by independent measurements using radio galaxy and quasar number counts, which probe the cosmic rest frame through different observational channels. Some analyses report a matter dipole, an anisotropy, in the distribution of distant radio sources that exceeds what kinematic effects alone would predict. If confirmed, this would suggest either a genuine large-scale anisotropy in the matter distribution or an unknown systematic in the observations. Nathan Seacrest, and collaborators have contributed to this debate with analyses of quasar catalogues, testing whether the observed dipole in source counts is consistent with the kinematic expectation. The results remain contested, with different catalogues, different selection criteria, and different analysis methods yielding different assessments of the tension. The debate mirrors, in structure, the bulk flow debate. The same underlying question, does the large-scale universe match our standard model, yields ambiguous answers when filtered through the complexities of real data. For our purposes, the CMB dipole remains the anchor. 620 kilometers per second, 2.232 million kilometers per hour. The local group moving through the CMB rest frame at a precisely measured speed in a precisely measured direction. The Dipole Repeller and the Shapley Attractor between them offer a dynamical explanation for that motion, a balance of pull and push, overdensity and underdensity, attraction and effective repulsion. The explanation aligns with standard physics. The details remain sensitive to data and methodology. The broad picture holds. The fine-grained questions stay open. The same dataset can yield high tension and no compelling tension depending on inference choices. An uncomfortable reminder of how indirect these measurements are. There is an analogy that the Cosmicflows literature uses, and it captures something important about how these structures are understood. Imagine a watershed, a landscape of hills and valleys with rain falling uniformly across the surface. Water flows downhill, converging into streams and rivers that drain toward the lowest points. The boundaries between drainage basins, the ridgelines, are places where a raindrop falling on one side drains east and a raindrop falling on the other side drains west. In the cosmic flow field, overdensities are the valleys, the basins of attraction where matter converges. Underdensities are the hilltops, the ridgelines from which matter flows away in all directions. The Dipole Repeller is, in this analogy, a hilltop. Not because anything is being generated there, not because any force originates from it, but because the surrounding landscape slopes away from it in every direction. The push is simply the shape of the gravitational terrain. The analogy has limits. The cosmic flow field operates in 3 dimensions, not 2. The landscape is defined in velocity potential space, not physical elevation. The field evolves over time as structure grows, and the reconstruction from which the landscape is inferred carries all the uncertainties and prior dependencies we have discussed. The intuition, though, is sound. Push and pull are not competing forces. They are 2 descriptions of the same gravitational potential, viewed from the perspective of overdensities and underdensities respectively. The dipole repeller repels because it occupies high ground in the potential landscape. The Shapley attractor attracts because it occupies low ground. The local group, positioned between them, flows downhill away from the void toward the mass. The dipole repeller remains. The Shapley attractor remains. The bulk flow persists at scales where standard predictions say it should be diminishing. The zone of avoidance still hides what it hides. The reconstructions improve with each Cosmicflows generation, and with each improvement, old certainties loosen and new questions emerge. 620 kilometers per second. The local group's speed, measured from the temperature of ancient light. The Dipole Repeller, roughly 750 million light-years away, contributing to the direction of that motion through the gravitational consequence of its emptiness. The Shapley Supercluster, 652 million light-years in the opposite direction, pulling with the weight of one of the densest concentrations of matter in the local universe. Between them, the Milky Way. Between them, the local group. Between them, us. Not pulled and pushed by forces we cannot understand. Pulled and pushed by the distribution of matter, by the presence and absence of mass, by the density contrasts of the cosmic web, by the same gravitational physics described by equations written more than a century ago. The physics is known, the map is incomplete, the measurement continues, the Cosmicflows program compiles distances, the Wiener filter reconstructs fields, the Hamiltonian Monte Carlo quantifies uncertainties, the bulk flow estimators debate amplitudes, the void statisticians develop new probes, the modified gravity theorists make predictions, the survey telescopes collect photons. Some questions may simply be beyond what science alone can address. The equations describe how density contrasts produce peculiar velocities. The observations confirm that the local group moves at 620 kilometers per second through the CMB rest frame. The reconstructions identify the structures, overdense and underdense, that account for the direction and magnitude of that motion. The question of why these particular structures exist in these particular positions, why the initial conditions took this specific form rather than any of the uncountably many statistically equivalent alternatives, that question does not have an answer in the physics literature. It may not have an answer accessible to physics at all. The Dipole Repeller sits in the reconstructed field, a divergent feature defined by absence, identified by reversed flow lines, positioned opposite Shapley, anti-aligned with the direction the local group has been traveling for billions of years, a void, not exotic, not mysterious in its physics, mysterious only in the way that all cosmological structure is mysterious, in the question of why this arrangement and not another, why these initial conditions, why this particular realization of the cosmic web from all the statistically equivalent possibilities. We have mapped our motion. We have identified the structures responsible. We have quantified the contributions from overdensities and underdensities, from attractors and repellers, from regions of excess mass and regions of deficit. The physics is standard. The methodology is sophisticated. The data grows. And still, the precise accounting depends on estimator choices, survey coverage, bias corrections, and reconstruction priors. The measurement is not complete. It may never be complete in the way that a laboratory measurement is complete, because the universe is not a controlled experiment. It is a single realization observed from a single vantage point, with instruments that see only what photons reach them. 620 kilometers per second, 2.232 million kilometers per hour, a speed that would carry you from the Earth to the Moon in 10 minutes and from the Earth to the Sun in 2.5 days. A speed that, sustained for 315 billion years, would barely cross the distance to the Shapley Supercluster. A speed produced by the combined gravitational influence of every density contrast within hundreds of millions of light years, including the excess mass of Shapley and the deficit mass of the Dipole Repeller. The evidence file remains open. The Dipole Repeller has been identified. Its direction is confirmed across multiple analyses. Its amplitude remains under refinement. Its connection to the broader questions of bulk flow, dynamical homogeneity, and cosmological model testing is active and unresolved. The Cosmicflows program continues. CF4++ has incorporated the first data from a new generation of instruments. The next compilations will add more. The map will sharpen. The uncertainties will narrow. The debates will either converge toward consensus or fracture into new questions. The Dipole Repeller, the Shapley Attractor, the local void, the Cosmicflows program, the bulk flow, the peculiar velocities of tens of thousands of galaxies, each one a subtraction, a redshift minus a distance, a deviation from the smooth expansion, a clue in a forensic accounting of cosmic motion. What we have then is this: a galaxy, the Milky Way, moving at 620 kilometers per second through the remnant radiation of the early universe. The motion is real, measured to within 15 kilometers per second by the Planck satellite. The direction is known. The cause is gravitational, the combined effect of every density contrast in the surrounding cosmic web, from the local void adjacent to our position, to the Great Attractor region at a few hundred million light-years, to the Shapley Supercluster at 652 million light-years, to the Dipole Repeller at roughly 750 million light-years in the opposite direction. The Cosmicflows program has mapped the flows. Cosmicflows 2 enabled the 2017 discovery. Cosmicflows 4, with 55,877 galaxy distances, expanded the map. CF4++, incorporating data from Wallaby, FAST, and DESI, extended the reach further still and reports that dynamical homogeneity is not reached at 200 to 300 megaparsecs per h. The Dipole Repeller is a feature in the reconstructed velocity field, a divergent region associated with a void, positioned opposite the Shapley Attractor, anti-aligned with the bulk flow to within a few percent. It is not anti-gravity. It is not a force. It is the dynamical signature of missing mass, a region where the gravitational acceleration falls weaker than the cosmic average, producing a net outward peculiar velocity that contributes to the direction and amplitude of the local group's motion. The same data that reveals the repeller also fuels active debate. Bulk flow amplitudes depend on estimator choices. Sub-sample composition affects the reconstructed field at large distances. The zone of avoidance hides structures that could alter the balance. Modified gravity models predict that voids should behave differently in certain theories, and surveys designed to test those predictions are underway. The Hubble tension may or may not be connected to local underdensities. The CMB dipole may or may not carry a small intrinsic component. R. Brent Tully, Yehuda Hoffman, Hélène Courtois, Daniel Pomarède, Aurélien Valade, Alexandra Dupuis, Noam Libeskind, Richard Watkins, Hume Feldman, Dale Koszewski, Harald Ebeling, Rian van der Weegaert, Alice Pisani, Nico Hamaus, the people who built the catalogues, developed the reconstruction methods, identified the basins and repellers, mapped the flows, and debated the significance of the results, each contributing one piece to a map that remains incomplete. DESI collects spectra from its 5,000 robotic fiber positioners. Wallaby surveys the sky in neutral hydrogen. FAST, the largest filled aperture radio telescope on Earth, contributes peculiar velocity data from HI observations. Euclid maps the sky from space. The Vera Rubin Observatory prepares to survey the southern hemisphere at unprecedented depth. Each instrument brings more distances, more redshifts, more peculiar velocities. Each narrows the uncertainties. None, by itself, resolves the debate. The number that sounds fast, 2 million kilometers per hour, barely moves the needle on the distance to Shapley. 315 billion years to cross a gap that light crosses in 652 million. The speed is enormous by human standards and negligible by cosmic ones. The structures that produce it span hundreds of millions of light years. The void that pushes us is defined by its emptiness, a region we can characterize only by the absence of what should be there. a repeller defined by missing matter, whose dynamical signature we infer from the deviations of tens of thousands of galaxies from the smooth expansion of space. The data accumulates. The debate continues. Not tragic, not triumphant, just unresolved. Good night.